Well, welcome everybody to our webinar today. We're recording these so everyone knows. We're posting the webinar recordings to YouTube so that we can share all this out. The webinar series, as you can see, contains a wealth of information about what we're doing at Blokable, from the business model to the manufacturing process to real estate. So it's a very deep series. We're hoping to use it as a way to kind of share the unique attributes of what we're doing and why it's different, and why we believe it's the real future and a path to solving housing. So here's the series. You can also see the series schedule on our website at blokable.com. It's in the news section. We posted something there so that you can register for any of the webinars along the way. And then we're also posting recordings once they're done, usually a few days after the fact, and we'll send out information about that. So today we're talking about the power of advanced manufacturing, and there's a few different elements to it. But largely, when we get into the presentation a bit more, you'll see this very methodical and disciplined process that we've been executing along the way to get from really early stage product development and prototyping through to advanced manufacturing, which is not a simple task and requires multiple steps. So today in the presentation, we'll go through scaling from industrialized construction to manufacturing, and then really talking a little bit about the learning effects of manufacturing and what an incredible opportunity it is to apply those into housing, and the meaning that that can have. And then also the path to the assembly line. So starting with the industrialized construction and manufacturing, what we'll talk about a little bit here is the sort of journey that we've been on to get the building system to a more mature place. If you look at every other industry that's sort of evolved its product into a state where it can utilize the benefits of advanced manufacturing, it has to go through extensive product development, prototyping, and stabilizing of the design and engineering in order to be able to leverage the effects of manufacturing. So we're many years, 6 years into that process at this point. The first stage that we had about a 30,000 square foot factory, and we were in Vancouver, Washington, really doing a lot of steel prototyping. So looking at the frame, putting the frame together, building out our initial roadshow model, really on a single sort of ADU type of structure, but very hand built, very manual, a lot of experimentation, looking at, how do you move these things down the line? Where can the beams be in a factory? A lot of logistics and layout for factory space, understanding throughput and what can the volume of a factory be. And we took that into the larger factory, the 60,000 square foot factory, where we did a lot more prototyping and built a number of projects, 4 projects altogether, including this one, which is the 12-unit project we built for Valley Cities in Auburn, Washington, which you can see a lot about on our website. But here we did a lot of material exploration. We worked with a lot of cold roll form steel, so light gauge steel, to create different elements of the build. We had a water jet machine that we used to cut precision components for kitchens and bathrooms, but we built a very precise assembly in a very repeatable process in a pretty manual way. But we validated a lot of what we were looking at in that stage, which was, what are the costs? What's the labor model? What are the materials? And can we have a precise assembly? But, we've gone light years from what this building was in building these prototypes out. If you look at what these looked like when they were going on site, these were all self-contained. So every one of these buildings was its own unique apartment. So we had studios and we had 1-bedrooms. But they were all independent apartments. So it was less of a building system at this point than it was sort of volumetric apartments, heavily overbuilt. These things were built like tanks, a lot of steel, very, very rugged, but a typical product development process, right? You sort of overbuild at the beginning, and then you learn to simplify through design and through engineering and get back to sort of the basics of what the product needs to be. And then also putting in the subsystems, right? So the key in that phase was also starting to roll out some of the subsystems that sit underneath the process, so that as you get to manufacturing, you have all the data that you need to really feed the machines. So the ability, as we were building out the building system, to start to say, all right, well, how do we How do we put all of this into 3D, put all this into Revit, connect it into our ERP system, and have it all ready for MRP? So that was kind of a quick background on some of the steps that we took, and you can see some of the milestones here that we achieved through these phases, which were, not trivial, but important through the overall cycle, which will make sense as we get into the next phases.
Aaron, I would add to that. So tanks, I guess what I would say is the first blocks, the very first one was a tank. The next ones were more like a Hummer, and the current model is more like a Ferrari. We took all the parts out. The thing is defined with perfection in terms of what's there, and the movement from the very first buildings into the current design. We moved out. I mean, just between the one that you're looking at there and the site built compared to what we have now, we've moved out about 40% of the parts, and the building is much more efficient than it was then. So it's a step-by-step process, making the most efficient build, and then engineering to something that's manufacturable.
Yeah. And then the key to that, the reason for that is to be able to access learning effects. So this is more a different sort of sequence through here, but looking at the difference between services and products from a cost perspective over time. Construction is a service. Construction is a, project by project service business that, is looking to meet the needs of each individual project. There's not a ton of standardization or repetition in it, not anywhere near the level of what we're talking about with our system, because our system is the driving force behind how we develop. But if you look at the general price rules around, what are the types of items that can be either stabilized or reduced in price over time, a lot of it has to do with being able to stabilize and standardize a manufacturing assembly to the point that you can really get into an assembly line process. And one of the things that we talk about, if you look at manufacturing, was, the Model T. There were other manufacturers, there were other car manufacturers at the time of the Model T who were also manufacturing, but they were still shifting their design, making changes. And so manufacturing could never really become all that efficient. And so by really focusing on stabilizing design, one dramatic example of that would be the dropping in sort of solar costs over time. Now, there's multiple sort of reasons for that, but if you look at one of the key elements to it, it's being able to really get into manufacturing and leverage economies of scale and being able to build something over and over and over again. And the way yeah.
Let me add something there, because I think that anybody listening, unless you're in the business, you wouldn't know really what it means. Car is easy to kind of stabilize and standardize because road widths are standard, bridge heights are standard, the low ones and the high ones, and you build to kind of a national roadway system, and everyone uses gasoline, so you've always got the same thing. The unique thing about real estate is that, number one, every state is different in terms of how they treat the real estate and their code requirements, but especially when you get to states that have unique conditions. And California is among the hardest because we have large earthquakes in California. You have big snow load. If you look at recent snow, is unbelievable load on roofs, and they can just collapse buildings. High winds are possible, soils conditions. So all these things make for kind of very unique site-specific builds in real estate that never happens in any other product. I think, and the other side of that, while you think you can standardize a product, I guess you could make a giant block that looks the same no matter where you put it. And that is manufacturable. And that has been an approach that some people have tried, but cities and people who like living in these things do not like walking down block after block after block of the exact same thing with no windows and no balconies. So the key is, how could you possibly build something that could be manufactured and still be as variable and as livable as something that was built on site? And that's what's very, very hard about housing, especially in California.
Yeah, totally. And then where we're getting to is some of this data and some of this analysis and looking at, well, how do we know this and what are the effects? The reason I pointed to the solar industry and some of these other, and the automobile industry, is from a manufacturing perspective, this is not new, right? So the industries that have reached a level of maturity where they've been able to move from sort of project by project, one-off job shop type of building into repeatable manufacturing. The lessons that have been learned from that are pretty clear, and the data is is well known and well studied. So our work with the National Renewable Energy Lab the output of that work was really to focus on, this roadmap and what are the implications of this roadmap. And the things when we were working with the National Renewable Energy Lab, the one thing that we had to communicate to them was what we were executing wasn't modular construction. And so our path to getting to scale required that we go through these different phases so that we could truly stabilize and really leverage the advantages of advanced manufacturing. And so when they were doing an analysis, the analysis was essentially if we can stabilize our product, stabilize our engineering through these phases of growth where industrialized construction is pretty much the same as short run prototyping in product manufacturing. But if you can reach that level of stability and then increase your volume based on what we've seen other industries move through in this same process, what are the types of effects that we can anticipate? And the numbers, when you start to look at the outcomes, and this is not with a huge amount of volume, this is imagining 10,000 units by the end of the decade, but the numbers are incredible, like a cost reduction of 45%, GHG reduction of 60%, construction material waste 91%, VMT 67%. These numbers are not achievable through, and NREL knows this, and this is what we've seen in studies, these numbers are simply not achievable in modular construction because you never reach the level of sophistication.
So Aaron, I will add, just in case people don't know, that probably already does, GHG, greenhouse gas emission. So the odd thing is a lot of people put time, money, effort, and a lot of talking about lowering greenhouse gas. And they might have a better air conditioner, they might have a better process of putting something together. But the fact is, the building has to be built on site. And when that happens, there's a whole lot of things going on. And it's not perfect in assembly, and you don't get the same output unless you actually take these things that are capable of being efficient and put them together in an efficient manner and process.
Yeah. And then there were different methodologies. This is a little nerdy, but they use different methodologies to take down the different elements. So the cost reduction had its own S-curve model, and then GHG had a little more complexity for those who wish to dive into the underlying methodological principles. But another element that we've seen a lot, which is really important based on the ramp up plan of moving from industrialized construction into manufacturing, is really considering the value of automation and when automation can be useful within the overall process. Because if you apply automation, and this is something we've seen throughout our growth as a company, was a lot of folks really investing in their factory capacity and their equipment and their automation before they had stabilized their product or stabilized their engineering. And so as a result, you get just way less benefit. You always get almost no benefit of automating something before you've stabilized it and maximize the value of that stabilization. So this is just sort of showing, when in the cycle, in the number of units that you're producing, and you can only get to the unit production through some amount of stabilization. And when in that cycle are you really going to be able to leverage value from the process of automation? And then looking at what those numbers look like for us, there's no, in the pre-build, the product development phase, you're not looking to build high volume. It's not that, and that's from a real estate perspective. What Nelson was talking about before adds a level of complexity, which is it's not easy to find small projects to build because small projects, you're trying to build a 10 unit or a 20 unit project. It's a lot more difficult to line up the factory capacity with the right size at the right time with the right amount of labor to solve problems for smaller projects and then grow into medium-sized projects and then grow into larger projects. So that's been an interesting challenge along the way, is finding the right factory capacity to do that. But if you look at the numbers in the early phases, you're not trying to build giant projects because giant projects don't give you standardization. They don't give you repeatability. You're trying to solve the problems of standardization and repeated builds on the size of projects that make sense given the complexity that you're taking down during that phase.
Aaron, let me add something very important to that, again, if you're not in the business, you wouldn't know. It's creating the solution, starting off on those smaller builds and making sure that everything you solve is scalable to code. You can't say, I'm going to go do something and have something really big and pray that you get code right, because that never works. You have to start from the premise that smallest thing has to be perfect and pass codes wherever you go. And again, it's not something that anyone should have a reason to know, but in the state of California, to build a building that's modular, before you build that building, you have to have an address for it because the code is specific to that address. So we can't go out and build 1,000 blocks and just drop them down wherever we want. It literally has to be built for the location. So you can't be wrong, and you have to satisfy whether you have high water table and dealing with the soils conditions and the water. And then you've got earthquake specific with the location, different types of earthquake conditions, up thrusts and all that. It's a lot of madness that you have to deal with.
And that's been the that's been a big challenge. I mean, a lot of companies that have gotten into building, even doing offsite construction or doing any type of manufacturing, I would just say be very skeptical of anybody who says that they're going to, build the buildings and then figure out the code later, because it just doesn't work that way, right? It just does not. Even when we were building our first ADUs, the questions were driven by code, right? What does the size need to be? What do the entrances need to be? How high are the cabinet? Like, there's all these questions that you have to answer from a code perspective, because otherwise, the thing in showing the Model T, pictures, the thing we've always said is we can figure out the most incredible assembly, the most incredible materials, and build, 10,000 of the most incredible buildings anybody's ever seen, and it would be illegal to put them anywhere because they weren't driven through a real estate process. So unless you're building through a real estate process, you have no idea what codes you're building to. And so, and then you have to wind all the way back to this pre-build product development phase process. You can't jump any of these steps. To get to this step, you have to have gotten this step right, and then this step right, and then that step, and that's what gets you to this S curve.
There's an important addition to that, Aaron, which is, even given that the West Coast in particular, I think California may have the largest number of unhoused people in the country as a percentage. Even given our numbers here, the state will not reduce the code for real estate. You have to pass the code. They do have temporary housing rules. They will allow people to take a shed that you can tear down later, and that happens, but there's also fires in those sheds because they're not built the same way. They're not meant to be permanent. They don't have to be hooked up and put on foundation the same way. But even with all those rules in place, the state itself cannot solve the housing crisis because it will not get rid of basic health and safety rules. And to build permanent real estate, they shouldn't. And to build a solution, it has to be permanent real estate because temporary facilities will not last, and they depreciate in value once you put them on your site. So it's a complicated process.
But what you see in this chart is essentially the classic S curve of manufacturing, which is you have significant early efficiencies, which we've already experienced in going from our initial builds to our second round of builds into our new building system, understanding our costs, the complexity. I mean, if you get the first products right, there's a ton of simplification that you can do to expand the capabilities of the building system and make it much more efficient to build. And so you see that early slope in the curve as you're solving, I would say it's sort of low-hanging fruit problems of simplifying the build, provided you've hit all of the code elements. And then there's a bit of a flattening as you're solving prototyping problems and assembly and manufacturing problems, preparing for advanced manufacturing. And then when you get into that advanced manufacturing phase again, you had another steep curve downward as you harvest a bunch of the effects of being able to do things like deploy automation and sub-assemblies.
Aaron, stay on the curve a second. What I'd point out is getting down that curve is more than just perfecting the way the building is designed and engineered. It's actually perfecting the market application also, because if you're going to build something that is high rise in California, the type of structural system that's required to withstand the what they call shear loads, and so buildings move around and dead loads and everything else in these huge buildings. That's a different frame system. It's a different finish. It's different labor. It's different manufacturing. It's different everything. To build single family, that's also a very different product. To print something single story, that's a different product. So you have to know what product you're building to. So for us, as we grew and found out all these limitations that each particular asset class placed on the manufacturing process, we actually determined that 5 stories over a podium is the one asset class that you could manufacture at great speed and have a design, a kind of an engineering and design structure that allows high flexibility, yet to be very standardized. when you get into high rise, it's a whole different game, and that is a different business, and people can service that, but that is not something that will solve the housing crisis.
Well, I don't know if you intended to do it, but that was an ideal segue because then we get into the process of like, how do you move from industrialized construction into an assembly line? Because that in itself is not just because you've built something like, and this is the state of the art for a lot of offsite construction or modular construction. You can build projects framing maybe a little bit more indoors to a certain level of completion for a limited market application and with limited opportunity to increase your productivity from there because that's simply an offsite construction process. To anticipate the transition from offsite construction or industrialized construction into manufacturing, there has to be an investment in the underlying product engineering that's going to unlock the manufacturing process. That has to be something that's anticipated and invested in and staffed and funded from the beginning to prepare for that phase, which is what we've done. And the core to it for our system is the structural joint and the structural assembly, which, and I'll, Nelson, let you go into
Yeah.
detail on this, but I mean, just at the core of it, it solves the two issues that we've been talking about, which is it solves the issue of the market application. Why is it the right answer to be able to deliver this market application that's going to yield the best properties, the best sites, the best rents, et cetera? But how is it also the baseline for an assembly line manufacturing process? So solving those two things with one innovation, we're very happy with where we've gotten to with this process.
Yeah. So if you look at that assembly, and it looks pretty simple, you look at the rectangles on the right-hand side of the screen, you think, well, what could that take? First, you have to understand why you'd want a rectangle to look like that. It seems simple, but if you look at the way current modular is built, they would have what we call a shear wall. And that's a thing that is put across that open space across the block. And when an earthquake hits, it keeps the block from crumbling and collapsing on itself and falling down in a giant pile. The other thing they can do is put bracing on the sides and between the columns and to support it so that as it moves around, it's strengthened, or some what we call tension rods, which again is used to stress the building and keep it together when an earthquake hits. However, if you want to be able to apply a standardized system across every asset class that you're building, or every asset type within the class, you have to be able to create 1 bedroom, 2 bedroom, giant living areas, co-living spaces, senior living spaces. They all have different layouts and different amenities to them. And as you start to change those amenities around and move the walls and rooms and everything else, all of a sudden all that bracing and shear wall limits what you can do, and you have to redesign your building every single time. And on the shear wall side of things, when you put something in the windows, as you've probably seen modular buildings that have a small window in them, or a small door, it's because there's shear wall in there keeping the building together. So we had to come up with a design that allowed us to be highly flexible through the entire rectangular frame and to have a window line that can go floor to ceiling glass or a full glass sliding door. And you'll see later in pictures that frame can also hold what we call a cantilever balcony. So we can put an 8-foot balcony off the end of one of these and still get through the code requirements in earthquake without the building collapsing and doing bad things. But then there's the question about, what can it really take? So the California code is actually designed so that citizens can live. It's not designed to protect the building. So if there's a big earthquake and the building is designed properly, everyone will survive. And in the worst case, the building is what we call red tagged. They require you to tear it down because it cannot be fixed. So given we have a model that focuses more on developing wealth and ownership, we actually came up with our own design, this resilient connection. And what the resilient connection does is it says, well, in a giant earthquake that would otherwise collapse a conventional connection or damage the building, how can we create a structure that at the end of the earthquake, we can fix it quickly and put it back in service? So that's what we created. I drew this up myself and worked with the engineers, and we created this small plate. You look at that bottom left-hand corner, it's got a small yellow plate on top. And that plate there, as the frame moves back and forth on its hinges, that plate will eventually pop when it's a big enough earthquake, but we can access that plate while the building is up and repair it and put the thing right back in service. And it doesn't seem like a lot, but it protects the equity in the building, number one. And also when there is a big quake, and I've been through a couple myself, Other buildings will be damaged, fall down, torn down, and people won't have a place to live. So I believe from a kind of community point of view, it's probably the best interest of the state that they increase the resiliency of buildings that are built in the future. And so we've got way ahead of that, and we filed a patent for that connection. We're the only one in the world to do this type of thing.
And then taking that from the sort of engineering and IP perspective into the sort of how do you fabricate this? What are the parts? How does it come together? How does it work? How does it go together with the rest of the building assembly to create, something that can be moved down a line from an assembly perspective where you've got this core chassis into which you can then drop precise sub-assemblies in a true assembly fashion.
Yeah, and I would add, if you look at that openness of that frame, again, it looks like just a simple rectangle. It is not. It has to hold the loads of everything above it. If you have common space in the roof deck, like a sun deck or a patio area, that changes the way the building behaves. That affects every block in the mass. Even the balconies I mentioned earlier, they affect the blocks. So all these had very specific engineering in every piece, so that when this thing moves, no matter where we put the building, it could be in Palm Springs or the San Andreas, it could be in Los Angeles, it could be in the Central Valley. This building behaves the same way and will survive. So that was very critical. But if you look at the big open space, that the floor and the ceiling come on, and it's what we call a diaphragm. It keeps the building, again, it helps it be strong in the event of an earthquake. It's unique to be able to put that together, put your bathrooms in with slope floors to run all your piping and everything you have to do, and to keep it simple and flexible. So that's what this assembly allows us to do in the end, is to have something that you just do an additive process like is happening right there in that video without having to change it. We could look at a site and say we want a wall in a different place, we want a bathroom in a different place, and we can move things around to make it highly variable. And even dropping in the HVAC on top, those are all kind of sub-assemblies that can drop in and make it much faster to assemble. Go ahead.
And maybe one of the more underappreciated facts, you look at the California market, I think it's five or six of the 10 most expensive rental markets in the country are in California. California as a state is the most undersupplied housing market in the country. It's also the highest barrier to entry market in the country, and it's largely because of these issues, right? So these issues, because of the safety requirements to be able to build in California and how those requirements are expressed in code, the difficulty of building in California is just unlike other markets. And so on the one side, it creates a barrier to entry to be able to do anything that's repeatable or standardized. Even if you could do it in other markets, you can't do it in California for the asset classes that are needed. But if you can get there, it changes everything. And so what we've done to make sure that our building system is built for the toughest codes in the country and accomplishes all of these from a manufacturing perspective is it knocks off the two biggest problems in the same brush, which is to say, well, how do you build in a standardized way for the toughest place to build in the country with the highest values in the country, but then also how do you do that using a manufacturing approach? So these buildings moving down the line, you start to see how if you can take a build and go from building in 6 months to 3 months to a month to a week to a day, suddenly your cost basis for building real estate changes dramatically. So it's ramping up the sort of production cycles and looking at different models for how the size of the factory relates to the ability to crank out more and more of these units that are standardized that can go to different projects. Obviously, this is where that earlier chart where we're showing the output now that we've reached that level of engineering sophistication, now we can start to phase in to the next phases where we can start to get to the point of really increasing the volume. And as Nelson was describing before, the key to it is the product that we manufacture results in very high value multifamily real estate. And so the floor plan capabilities that we have with the system because of the structural system and because of the assembly means that we can build in markets where you would otherwise never see anything modular or prefabricated. The buildings that we can put in place in prime high rent markets with beautiful floor plans, where at the end of the day, the people living in the buildings probably won't even know that they're modular. They just know that they're beautiful apartments. are unlike sort of any other system that you could put in place in order to be able to develop. And so as the video continues, you'll see some of the applications that we can build for, which are unique and extremely high value because of the manufacturing systems that we've created with the engineering.
I would add, as you see that those blocks going together, you can see that the blocks don't create just a flat front, and those aren't full fronts. The building actually articulates, moves back and forth, and actually it makes it more livable. It makes it much more pleasant to the eye, and most communities do not like massive flat buildings everywhere. So it's the ability to create this kind of normal looking building that you would build on the site typically, yet have the standardization of a modular approach.
So you see some of the different applications here, and here, you can see that's a project that was that we have in pre-app in Sacramento. This is a West Sacramento site. The other one was an LA site. This was actually a Washington State site. So you can see the context and the architecture and the community context really change through some of these, and see just the wide variety of application you can see. And then dialing all of that back to the original ramp up chart, you can kind of see how all these things work together, where we go through these phases of stabilization on the product and on the engineering, on the manufacturing perspective, and then how that results in flexibility on the real estate side. And so what we're really doing is synchronizing manufacturing with real estate development, which is something nobody's ever done before. Usually the factory sets itself up and it's selling to developers, and however many customers there are on the pipeline, which right now for a lot of factories is very few, then you end up with this process, which is really what the manufacturing has to do, is to service the real estate development process, because the value of being able to reach these types of cost reductions on the manufacturing side alone is hugely valuable from the perspective of being able to build the real estate more efficiently and own it over time.
Yeah, I'd have to add to that the fact is the reason I want to be a developer really is because only a developer is going to know what he needs to change, or they need to change, to be variable enough in all the markets they go to. So if you went to a modular builder, he would build what an architect tells them to build. That's not a good thing, because you're not thinking, wow, there's like 50 variations on that one room that I have to deal with. So what is the design change I can make that will work in all 50? Well, you're not going to know until you do all 50, and then those go back and do them all again as they're told to do them. We actually have to think through that variability and be able to look at it and say, if we change the room size, and we change the room depth, if we change the windows, if we change how anything is moved around the HVAC, what does it do to our building? And how do we still put it together without changing the factory line? And that's really the unique thing about the structure, is to be able to standardize it, yet being highly variable in application.
So that's the end of the presentation part of it. If there's any questions, please feel free to put them into the Q&A. We've got the Q&A loaded up here. We'll give everybody a few minutes if they want to ask any questions. If not, we'll wrap it up early and give everybody some time back.
It's Friday.
Yeah, exactly. Well, we must have done an extremely thorough job because there are no questions coming through in the poll. So with that, we're gonna wrap it up. We'll post this and send post webinar emails around to the folks who attended. Oh, we've got one person with their hand up. So if you could drop your question into the chat, that'll probably be easier. Or why don't you just go ahead and talk? It's for Steve. You're muted.
Hello,
Steve. If you're trying to talk.
Yeah, he's still on mute. You put it in the Q&A. There you go. Why choose steel versus wood for 5 over? Yeah, it's a good question. There's a lot of reasons for it. Number one, wood, it's got its benefits, it's got its problems. To have something that's long and straight and to be able to build to tight tolerances in modular wood, it costs a bit more money, takes a bit more time, and so that's something that you have to deal with. But more fundamentally, to build with wood, you need to put shear wall, because it doesn't have the structural integrity with the beam sizes we have. If those were wood, you can imagine what would happen if we picked it up, it would collapse. So as you move into a high earthquake area, You'll notice that your window lines will get squeezed in, your doors will be squeezed. You won't have the big open spaces. Cantilevering off of a wood structure in the way we do it wouldn't happen without some serious structural support somewhere. The interior of the space, if we were building one, twos, threes, switching it over to from a 350 rent in the Valley in Los Angeles area out to a $6 rent in Orange County or La Jolla or Santa Monica, all of a sudden you're changing those designs and layouts in the open space. And now we have to re-engineer the entire building because those shear walls and all that structural support has to be designed for that build. Our build, because of the way it is, we have from the window line to the first column can be up to 21 and a half, 22 feet. So you can imagine the variation we have in our layouts. And we don't have any load-bearing walls in the building. So that means we can change everything and put it together any way we want. And we can have massive open spaces with no big headers required and no changing or structural support added, which is why it's very important for us to be the first ones to create that structural joint. They got rid of the shear wall, the bracing, and the tension rods. You cannot do that with wood. So what that means is on supply chain side in the manufacturing, we can order the same steel because our steel thicknesses, we know exactly where they are and what they are, and they do not change. The length changes as we shorten the rectangular module, but that's it. We also know that our structural hoops, that we call them, those hoops are not going to change because of how they perform and what they are. So we could advance manufacture those. It wouldn't matter where they're going. They fit on any site. And we can get ahead and get forwards on all those supply chain issues, even the flooring and everything else that we do on our walls. So while we may not know exactly what we're building on every single site ahead of time because you don't know the site, but what we can do is get a steady supply chain that's always there and get forwards on long commitments on those items that we know take time to get. Can't do that on something that has to be designed for the site. So there's a very, very good reason for it. Also, from a kind of a green point of view, we've seen a lot of things where kind of odd life cycle analysis of wood structures, and they said, oh, it's great to cut down trees and put it into a building. Well, let's just tell you that isn't true. When you cut down a tree, you've got to replace it with the tree. And for the first 10 to 20 years, it actually puts carbon out. People weren't accounting for that properly. And then wood is organic and it eventually breaks down. So in life cycle analysis, wood puts carbon back in the atmosphere. Green steel is now very real, and very shortly you have very green steel coming out. There's some new things that are happening. So the greenest building you'll be able to build will be out of steel and better life cycle. But let me add one thing too. It performs better in kind of varying conditions. So we can throw it in the snow, we can put it into the sun, we can let it shrink and contract in extreme conditions. We can do a lot of things to it, and steel doesn't kind of age hard and get damaged by shrinking and expanding and shrinking, expanding and popping. So it's a much more resilient building.
I mean, we have one of our buildings that's up at the National Renewable Energy Lab that's been craned 11 times. I mean, it's been craned up and down, moved, put on trucks. It's been trucked thousands of miles. It's gone through the Rockies. It's been down in the, fires in the Bay Area. It's been all over the place, and it just keeps on. It keeps on moving with no issues whatsoever. So they're very, very durable, very long-term useful life. They're just higher value, I think, is another good point from the long-term perspective of the real estate ownership is having a steel building simply is a really great asset to own over time.
I'd also add, just from the developer, I am a developer. I have over 1 million square foot of real estate, half in for-profit, half in not-for-profit. To be able to look at a site and mass it on day one, to know exactly what we're going to build, to be able to pull out working drawings in a fraction of the time I could do in any other build, and to know that with certainty all those supplies are at hand. I can't accomplish that with wood, because with wood I'd have to go in and design for the particular site, design those shear walls and the bracing, everything else I need for that build. We'd have to hire the architects and engineers and take the time to do it. There'd be a greater upfront cost in pre-development. When you get to the design drawings, and you got to worry about getting to your working drawings and get it nailed down. That's all cost. So our goal is to get rid of the soft costs, get rid of the architect, get rid of the engineer, and make them work on making the thing applicable to the site, not to designing and engineering the building for the site every time. That's a big waste of money and time.
So it's a perfect wrap up, because all that basically means that there's no way that you can really get to truly advanced manufacturing with that process, because you don't have the level of standardization that you would need to build the real estate. So, oh, there's one more question that's popped in.
Nope. No, he said thank you.
Oh, to quote, love the compliments.
No, there
Okay.
is another question. Hang on a second. There is one.
Yep. Yeah, so we can't really talk about the investment on the webinars. So the best thing to do is to send an email to invest@blokable.com, and we can respond directly with any of the questions regarding investment. So if you could just send us the email, then we'll be happy to respond, but we can't do it in the webinar. So with that, thank you very much for attending. Appreciate it. We'll post this to YouTube, and the webinar series will continue. There's some great topics coming up. So check on the website, check the schedule, and I believe our next one is next Wednesday, and then we're going to go to a Friday Ask Me Anything format, which who knows what that'll open up, but that should be fun. So thanks for your time. Bye-bye.
All right. Good weekend.